Welcome to the lecture on recombination in the course of Physics of Solar Energy Conversion. We have the picture of the semiconductor in equilibrium with the equilibrium Fermi level. In this case, this is P-type material, and it has plenty of holes and a few electrons in the conduction band. Now, if we pump in some carriers, for example, by illumination, then we generate minority carriers, and then there would be a lot of electrons available in the conduction band, and there is a splitting of the Fermi level, so the system is not in equilibrium. So then there will be a recombination process in which an electron in the conduction band returns to an empty level so that an electron-hole pair is annihilated. And this process is the band-to-band recombination, and the energy of the pair is converted into a photon. So this is called radiative recombination because then the semiconductor is emitting light. And this is the reciprocal process of the light absorption in the semiconductor. There are other types of recombination, and especially this is important when there are trap or localized levels in the bandgap. So the trap interacts with the bands so that, for example, this level can get an electron, but then it will release again the electron. And a level close to the valence band edge will capture a hole and release the hole. So we can have like trap limited transport because there are plenty of electrons in the conduction band, and as they move, they are being trapped and released. So traps are very important in semiconductors that have some disorder. And a especially important process is a level of trapping that is near the middle of the bandgap. And this is called a recombination center because it can take an electron and take a hole. And this energy is not released as a photon, but it's rather turned into heat in the lattice. This process is called the Shockley-Read-Hall recombination. And then in a semiconductor with a recombination center, we can have radiative recombination, band-to-band, or we can have trapping of electrons and holes in the intermediate level, and then this will be non-radiative recombination. So in semiconductors, there are three main processes. One is radiative recombination, the other is Shockley-Read-Hall, mediated by traps, and the other is a three-body collision process that is called Auger recombination that happens when there are a lot of carriers in the sample. The process we just described are the bulk recombination in the semiconductor, but in a solar cell, we have, in addition, the contacts, and this is an important place for recombination because at the termination of the semiconductor, at the surface, there are specific trap levels or formed either by the termination of the semiconductor or by the interaction with the metal. So surface recombination is normally an important effect. So here is, for example, different candidates for contact to the perovskite, and according to the matching of energy levels, here is an injection from the electron contact layer, an injection of holes from the valence band of the perovskite to an interface level. And this can be suppressed if the system introduces an additional barrier that avoids this type of recombination. In the semiconductor electrolyte interface, we have injection of electrons to the acceptor oxidized levels in solution. But then we can have also electron traps here, and this is a site of recombination with holes because here the electrons are immobile, and these levels can also inject carriers to the solution. There is an important question, which is the time scale for recombination. Here, as discussed before, we have generated electrons in the conduction band, and they are non-equilibrium electrons, so this Fermi level in the end has to come down to the equilibrium value. But how long takes this process? So this is described by the carrier lifetime, normally called tau. To measure the carrier lifetime, we start with a steady state situation. Here, for example, there can be photogeneration maintaining a separation of Fermi levels, and then we introduce an additional pulse of carriers. This creates a step of the Fermi level, and this is going to come down by recombination after the pulse, so that the evolution of this step will be the initial value and some type of exponential decay. So this tau is the characteristic lifetime of recombination at this particular steady state. Measuring the recombination time, the carrier lifetime, is a very important step for characterizing the operation of a semiconductor, and there is a large variety of methods. So there can be optical measurement based on the transient decay, observing, for example, the photoluminescence intensity of the pulse, how it decays. And there can be also electrical measurement, which is measuring the transient of the voltage. So here there are different examples of PL decays. So this is log linear plot. So this is a very good exponential. And the different decay rates are due to the change of the contact that is affecting the surface or recombination rates in this sample. By this method, one can make a picture of the dominant recombination process for a semiconductor. Here we see the silicon recombination. This is dominated Shockley-Read-Hall, but at higher carrier densities, this is controlled by Auger recombination.